Well, hello and welcome. I'm Jeffrey Sarnoff, and I'm here to talk about fast floats for deep learning. The IEEE has a working group charged with developing small format floats for this purpose, and I am honored to be editor-in-chief. I'm going to discuss these families, the nature of the floats themselves. This is not a talk about how to use them. It's a talk about how they come to be made numeric. So the first thing that we did is the top part, the signed, and then eventually it occurred to us that for block floating point operations where you have a block of numbers and they're all scaled by the same single value, unsigned was very helpful and appropriate. There are four families, and two are signed, two are unsigned. All of the families have a single nan, and the families are split between the finite and extended versions, the extended versions having support for infinity. I took the work of the committee, which is still not, it's not a standard. It's not a standard until the IEEE says it's a standard, so everything I say, take it with a grain of salt, although we've been at this for a couple of years now. So I wrote software to model and test and make sure that what we were doing from the perspective of a software architect was reasonable and better than reasonable, made life easier, and had no hidden problems. That was a repeated effort because it's a standard in development, things change. But we do have these families, and there is a way they are named. It comports with IEEE 754, which is the long-time standard for floating point arithmetic. Starts the word binary, then you have the number of bits, followed by P for precision, the number of bits of precision. And as you see up on over there, the suffixes to determine which family you're dealing with. Now, a lot of this is my own artifice, but fairly reflects what's known about the work of the committee. All right, so these are not your ordinary familiar floats. There are some major differences. One is we have only one zero. There's no negative zero. And we have only one nan. There are not many nans because, well, part of it's stylistic and part of it is there are just fewer code points to deal with, so one has to be careful about how they're used. Another big change is we've ruled out having exceptions. So this is because of the nature of the workflow in deep learning. You have massive amounts of work and resources taking a lot of time, days, weeks, months, and you just can't be in the business of interrupting what you're doing because of some exception, trying to deal with it and coming back. It just slows everything down tremendously, and it makes thinking about how to do it much harder. So we got rid of them. Now, implementations are allowed to provide their own additions, whatever, but they can't use the names that are used in the standard, and they have to specify exactly what it is they're doing. The abstraction hierarchy, and I lean a lot on the abstract. I'm going to be revisiting this. The abstraction hierarchy follows directly from the diagram of the families, and the names accordingly. The AKO names, the AKO is for a kind of, and those are my leaf abstractions. The structs themselves get use those leaf abstractions as their superclass. What is so very nice about using the abstractions is being able to compute over them, because generally it's a simpler approach, fewer headaches when you can do it and it works. In this case, all of the abstractions that for these families carry the, as parameters, bits and the precision. And it turns out that that's really enough, well, it's certainly enough to derive other critical descriptors of a member of one of the families, and it's enough to get a great deal of the work done. Some simple examples are, you can certainly figure out how many values you've got, how many fractional bits, and the last one, the bits in the exponent, it has that the term is unsigned, because for unsigned floats you don't need the sign bit. That sign bit gets put into the exponent for additional dynamic range. So from any abstract leaf, we can construct the float per se. And I use AI float as our generic interface. With the abstractions, you just put in the leaf abstraction and you will get back the encoding and the float values that match to each encoded value. You can do the same thing concretely using the essential parts of the float that you're intending, giving the bit width and the precision, and then whether it's signed or unsigned, and whether or not it's finite or extended, and you get the same thing. Well, that's interesting. Here we go. Do it the old-fashioned way. So what I found in going through this, and it's not, it presents as not a lot of work. In fact, it was 6 full revisions before I got to where I really was comfortable with it. And one of the things I found is that this mixing of abstract and concrete in a way that you didn't have to think about it, because if it worked one way, it works the other, was really opening for a lot of possibilities. Here, the AI with a little soccer ball just stands for abstract AI float, because it doesn't fit to put it all in. And it is true that anything that can be addressed, given a concretized or realized version of one of the entries in a family, can be done abstractly, and vice versa. And this is where things really start to shine here, because after writing up the logic for the abstractions, to get it to work with the actuals, the realizations, this is all that's required. And it's just the 3 lines of code. And it works. Families have invariants, things that are true regardless of whether you're talking about a 3-bit float or a 15-bit float. Let me take a moment to expound on that. We're covering floats where the total bit width is as small as 3 bits to as wide as 15 bits. 16 bits and above is currently with the other standards group. And for those, you can have all of the precisions that are available you can use. For signed types, the precision ends up, you can't have the precision be the same as the bit width, because odd things happen mathematically, but you can for unsigned. So there are a lot of things to choose from. And one chooses, presumably, to maximize the effectiveness in whatever application is involved. A conforming implementation does not need to provide all of those floats. It can provide as few as one of them. Will tend to provide more than one, but there's really no expectation that everybody is going to spend transistor resources to make sure all of the possibilities are available. It will be kind of target dependent. So we can go from the number of magnitudes, which is, magnitude is essentially the absolute value, and using that, that turns out to be very handy in figuring out other things. And it's up here on the screen so that I can point out the kind of symmetry of a sort between the unsigned and signed here, where in each case you take the number of values and you do something involving 1 with it. In one case you subtract the 1, in the other case you shift down by 1, but it's a shifting is essentially multiplication, right? So you have the two kinds of basic arithmetic operations shown in the world of the unsigns and the world of the signs. Similarly, if you want to know what code point your nan is at, you can find that out, or your 1, you can find that out. There's a fair amount of discussion about the utility or disutility of subnormal values. These are tiny numbers, and some people argue that, well, there's overhead and they're slow and I don't really need them, and they quash them to 0. And other people feel differently. It used to be the case that subnormals did take more time. That hardware manufacturers have gotten very good at that now, and there's really not much cost to it. They're also, well, which side do you want to go down, right? There's subnormals are smoother. Your gradient stuff is more nicely behaved. Sliding down the rocks is not so good. And just a point of art, subnormal 0 is not considered a subnormal. When you take the count of the number of values that are subnormal, because 0 isn't in there, it throws off a lot of other stuff down the line. So I've coined, and please promulgate the term prenormal to include 0 with the subnormals. It makes a lot of the computing that takes that into account easier. You do want to be able to quickly identify where do my normal numbers start, where do they end. Infinity is also not a normal. And in, pardon? Is it post-normal? You bet. You bet. So we can find that out. You want to know in lots of kinds of analyses whether you're dealing with a normal value or not, and by looking at the code point, the code points directly encode the values. The way I'm talking about is the values are a separate group of, piece of an array or something, but it certainly is not, doesn't have to be that way, and often isn't, because when you're working with the code points, the directly encoded values, you can do some pretty amazing stuff. You can take the most complicated, highly graduate level, PhD level, univariate expression you like, right? And you can put all of the answers into a small table, because these are small numbers of values for each kind, so that you can then cascade transformations just by going from one piece of a small table to the next, like daisy chaining the direct encodings, and that's a big deal. All right, we have, this will be, when it's approved, it will be the first standard, international, well, national or international standard, that has formal verification with it at its introduction. Uh, this is very comforting. Linus will tell you. It means that you don't have to be concerned about watching out for nans when they may occur, when they pop up, because they'll only arise where they're specified to occur, and they cannot arise anywhere, and that's been formally verified. We have the proof. Similarly with infinities, and a sequelae is that the floating point operations themselves will comport with their specifications. They're not going to go, there are not uncovered edge cases, as it were. So that means that when using this formulation, you can take it easier. There's not bad stuff that you have to worry about that you don't bring to, unless you bring it to this. A brief look at the specification. It's not really, the details are not important. What's important is that all of the things that are specified, the parameters are listed, the operands, the output, and its behavior is characterized. And also, here's addition. I'm not going to go into the details. What is of note here is if you look up at the signature, you see the fx, fy, and fz. It means that each input can be of its own format. Again, we don't require that a conforming implementation support all possible combinations. They can, pick one or two. That's perfectly fine. But the specification itself covers all combinations. And the last item of note is the pi symbol used for projection. Projection means it combines both rounding and it combines capping, as it were, getting rid of the infinities, closing the domain to infinity, so that you're in deep learning, you don't, there are many times where an infinity showing up is not going to be helpful, and it's much easier to have the computation roll on if you're dealing with normal values. So we roll those into one. And more details. We have two groups, larger groups of numbers. The extended reals is something that's been used a lot. It's the real numbers plus infinity. We introduced the augmented reals, which is that and nan again attached. It turns out that particularly in proving things, it becomes simpler to use the augmented reals. I'm sure this is a familiar picture. And the point is just to reorient one's thought to the bit fields, because we're going to go into that. On the top are the role of the exponent, on the bottom the role of the significand, and just note that the first two rectangles have the same outer color, and that the second, third, and fourth squares do. Because I think of them as spans and cycles. The exponents span each cycle. The cycle incorporates all possible fractional bit patterns. Here it's shown with 2, but there could be as many as there are significant bits. And the span, the exponent, here you see them valued as if it were the raw bit field, and then subtracting the bias, so that this allows exponents to be both positive and negative, which is useful because you want to be able to grow and shrink things. The only unusual part here is these little steps that take the -1 and put it on top of the -2. That's because this first column is for the subnormals, and for technical reasons, the subnormals need to have the same exponent as the initial normals. These things, the bias brings things more into balance, and exponents are computed as by taking 2 to the number that is the exponent, with the cycles are the fractional bits, and here you see the broken into subnormals and normals. The subnormals, you get no implicit bit added to them. The normals get a 1 added to them. And you see on the bottom row the significand values that result. Then to actually get the value, the binary rational that you're going to compute with, you multiply the exponent and the significand, and the lower row gives you that. You see that at the very end, nan is overtaking the last position because all of our representations have a nan, and this is unsigned, so nan goes at the end. For signed, it's between the positives and the negatives. And let me close with this. I've been using Julia for a very long time, long before anybody ever thought there would be a version 0. This, it's been quite helpful to me. I threw away all my other programming languages. I thought about what I had come to learn about how best to work with Julia and how best to have Julia, let Julia work with me. This is the result of 14 years of experience with Julia, and here we are at JuliaCon. Please take it as my best information. Thank you.
Covering for the chair of this session, and thanks for the fascinating talk. Any questions for Jeff? We have plenty of time.
All right. Yeah, Alan.
Are there any existing? I kind of like the method where the person on the at the podium just repeats the question, but you always have to remind them.
Thank you.
Because nobody ever remembers to repeat the question. So I'm just wondering if there are any existing formats made by any chips that don't fit into your
Well, so the question is, are there any existing formats made by current manufacturers that differ from this? And the answer is all of them, right? Because this IEEE standards drafting group, came to be after a bunch of those things were around, and we are specifically charged with not feeling overly bound by what's there. Our charge, we have representatives from industry and academia and people like me. We have worked very hard to do the best for the future user of the standard and not be too worried about the present stuff. Now, there are people on the group who have a lot of experience with this, and well, if you're doing some of what's out there now, doing this is not such a stretch, but no, there is no like this now. Yep.
Thanks for the interesting talk.
Yeah.
So if I understood correctly, then quantization will be almost trivial in this setup.
Well, you won't have to worry about it, but certainly an implementer will have to. It happens, the math is happening in a math place, and it's being projected into the format of your choosing, and that's done given whatever rounding and saturation kind of setting that you want to apply. So that's all that the client need to be concerned with, and yeah, it'll all work. The implementer has to make sure that it work right.
But the computation will only happen on the data type level, right? So if I
Yes,
train something
the question is, so the computation basically happens on the data type, and the answer is yes. And in large part, and wherever possible, we have sought to simplify things.
As kind of a follow-up to the first question, when do you want to when do you think, or do you think that the industry standard will become the same as the IEEE that you just presented?
I can speak from history. 754 was in much the same position. There were lots of competing versions of how to do floating point arithmetic and what floating point values were. And there was, you can look at the records, there was a lot of concern about, will industry adopt that? Well, it did. And, you know, industry will do as it feels is best for it. However, I would not have put in the time that I've put in and the focus that I have given this if I thought that it would not be, there would be no fruition.
Do you have a modern day Kahan to beat everyone under the table?
I have better than that. I have, I don't know how to repeat it. Loosely, it was, do I have a subtle way of influencing industry to adopt this? And the answer is, I don't, but their clients do. And clients, big clients, say, I need something that comports with the standard because that's what my customers demand. And this is going to be it. A client who wants two vendors can have two vendors. A client who wants to develop their own chips can develop their own chips. This isn't proscriptive, it's prescriptive.
Yeah, we still have a few minutes for more questions.
Just very quickly, what were the languages you threw away?
Oh, that's a great question. So, I once wrote a resume that listed all of the languages with which I had experience, and I was able to do one for every letter of the alphabet. So many, many. Julia really gives me a sense of comfortableness in the using that I remember this from one of the first JuliaCons. We were asking people, what made you come to Julia? And everybody's answer was, I'm just so tired of the tears that came with using, you know, massive C++ or Fortran projects. And it is a world of difference. Yeah, that's my answer.
All right, let's